Hi everybody, welcome to the section 4.2 video. In this video, we're going to be talking about reduction of order. And so what reduction of order is, let's take a look at the learning objective, is using a single solution given to us to find a second solution to a second order differential equation. So we are trying to find a second solution, y2, with y1 given to us. And so we're dealing with second order linear homogeneous differential equation. And as we've seen that this is our second order linear differential equation, and solutions to this type of differential equation is a linear combination of this form. Y equals some constant C1 times a solution Y1 plus a constant C2 times a function Y2. And we've seen that Y1 and Y2 need to be linearly independent. So in the next topic, next section, we're going to learn of a method for determining these solutions when coefficients of this second order differential equation are constant. So like A2, A1, A0 are constants. Okay, so when we get there, it's a straightforward, exercise in algebra. We'll have a quadratic function, we'll factor it, and get our constants. But in some cases, this straightforward process breaks down. And when the process breaks down, what it does is only gives us a single solution, y1, to this second order differential equation. And so when we're given a single solution, we need that second solution. And so there's a way to construct the second solution if we know the first given solution, y1. Okay, so the basic idea and background of this section is that the second order linear equation can be reduced to a first order differential equation by substitution involving our known solution y sub 1 that we obtained. And so we can use our given solution y1, use our substitution, and a second solution is apparent. This is where reduction of order comes in. So we're given our general second order linear homogeneous differential equation. We know what y1 is, we know that solution, and we seek a second solution, y2, to fill out our general solution to this DE. And that's where reduction of order can help us get y2, that second solution. So the entire reduction of order process can be a long, drawn out process. It can be a long problem to solve. But what we typically use is this shortcut right here. So given a first solution, y1, we seek to find a second solution. And so what we would use is y2 equals y1 times the integral of e to the negative p of x dx divided by the first solution, y1 squared. Okay, so a couple things look a little familiar, right? This e to the negative p of x, that looks a little familiar to us. That right there is the integrating factor from our linear setup and from our Bernoulli setup differential equation. And so here we're dealing with the second order differential equation, so it wouldn't be attached to just the y. For our second order, it would actually be attached to the y prime. So it would be that a1x attached to the y prime. Okay, so we have our reduction order formula to get y2. Let's go ahead and try an example and see how this works. So finding a second solution using the reduction of order formula. So for the function y1 equals x squared, that's our first solution of the differential equation, x squared y double prime minus 3xy prime plus 4y equals 0. We want to find the general solution of the differential equation. So what that's asking us is to find that second solution, y2. So let's go ahead and try to find the second solution. So here we go, solution. We are given that y1 equals x squared. We want to find what y2 is. So we're going to use the reduction of order formula, y2 equals y1 times the integral e to the negative p of x dx all over y1 squared times dx. So if you could recall from linear or Bernoulli work that whenever we get started with an integrating factor, what we need to do always is put the differential equation into standard form to get p of x for our integrating factor. So in other words, get y double prime naked. So what we're going to do is divide x squared to both sides. So if I divide x squared to both sides, what I get is y double prime minus 3x over x squared, y prime, plus 4y over x squared equals just 0. Okay, so let's clean this up a bit. I want to simplify, cancel a couple things out, and move a couple things around. So we get y double prime minus 3 over x y prime plus, I'm going to move this x squared and 4 in front of the y, and it equals 0. Okay, so what we have here is our p of x, and just for good practice, this would be our q of x. So let's go ahead and get that integrating factor now, since we have p of x. So e to the negative integral of p of x dx, well, that equals e to the negative integral of negative 3x, 3 over x dx. And so two negatives make a positive. And so that would be e to the natural log, absolute value of x. We need to move that 3 up to the power so that the e and natural log could cancel out. And so what we're left with is x cubed. So we have our integrating factor. So now back to the formula. So we'll say formula time. We have y2 equals, I'm going to rewrite it again, y1 times the integral of e to the negative p of x dx over y1 squared dx. So if we plug everything in, y1 is x squared from up above times the integral of x cubed over y1 squared, so x squared squared dx. Here I'll say like note y1 equals x squared given. Okay, so this turns into x squared times the integral of x cubed over x to the fourth dx. This simplifies to 1 over x. So I have x squared, 1 over x dx. And x squared, 1 over x turns into the natural log, absolute value of x. And so this right here is my second solution. And just be a little careful with the interval of solution. Because of the natural log, we need our interval of solution to be 0 to 8, or 0 to infinity. But this is our y2. So we finally have our general solution. Remember, general solution is y equals C1 y1 plus C2 y2. We have our y1, we have our y2. And so we have y equals C1 x squared plus C2 x squared natural log of x. Okay, so we got our second solution given our first solution using the reduction of order formula. So it comes in handy quite well. Uh, it's a long drawn out process if we were to take a different route, but we want to keep it simple here, just use the formula. Um, and so hopefully this helped, and thank you for watching, and I'll see you in the next video. Okay, take care.